Well, hello pre-calculus students and general seekers of truth. In this video, we will talk about applications of exponential functions and logarithmic functions and logarithmic equations in particular. And let's start with some vocabulary. Now, one of the very common types of exponential function application is called exponential growth. And so you have a situation where a function is an exponential growth if you have in a function in this form: a times b to the x. A and b are both real numbers, and more importantly, b is some number that is greater than 1. Okay? So to get a better sense of that, let's see what happens if we were to graph something that is, where the base here is a positive number that is greater than 1. And you can graph just about any function you like with that description. It's going to be pretty clear that this is what it will look like. So, just for the sake of the argument, let's graph like f of x equals 3 times 2 to the x. Okay? And without going into too much of the detail, you can look this on a graphing calculator, and I guarantee that it's going to look something like that. Probably be smoother than the curve that I drew. In fact, let's see if I can do that just a little bit better. Okay, so it's going to look something like this. In other words, as x gets bigger, f of x will get bigger, and as x goes towards negative infinity, f of x will level off towards 0. So we can define exponential growth as having some of these characteristics in terms of limits. As x goes towards infinity, f of x will approach infinity, and as x goes towards negative infinity, f of x will go towards 0. So that's an example of exponential growth. Now, another common example analogous to this is exponential decay. Okay, so an exponential decay function is in the form f of x equals a times b to the x, where b is a proper fraction or a decimal that is positive but less than 1. And it's not hard to imagine what this function would look like, so I will do a quick sketch of this for you as well. And it's sort of the quote-unquote inverted version of exponential growth. So as x gets, let me get that a better curve here. So as x gets more and more positive, or larger and larger towards infinity, f of x will level off at 0. So we can define it this way. So as x goes towards infinity, f of x will level off at 0. And as x goes towards negative infinity, f of x will continue to increase towards positive infinity. In both of these cases, there is a concept called the growth rate and the decay rate. So the growth rate is b minus 1, and it is often expressed as a percentage. And here the decay rate would be 1 minus b. So let me show you what I mean. So let's say we have a function. Let's call this, let's give this an example. H of x is equal to 5 times 1.25 to the x. Okay. Well, this is exponential growth because b here is the base here is larger than 1, so this is a growth function. And in particular, its growth rate is 1.25 minus 1, as what we defined earlier, or 0.25. And oftentimes in real applications, this will be described as a percentage. So this will be 25%. Okay? However, whichever version of this you prefer to use, they are both correct. Another version of this, let's look at a decay. So what if I have like 200 times 0.93 to the x? Well, in this case, this is a decay function because the base here that's being repeatedly multiplied is less than 1. So a decay rate here would be 1 minus 0.93, or we can, work out the math. That's 0.07. And again, this is often described in a percentage as 7%. So some very, very gentle introduction here into the world of exponential function applications. In the next video, we will take a look at some more specific examples with money and interest rates and all of that good stuff. As always, thank you for watching and have a wonderful day.